and it's publicly accessible. However, it's not really designed for public use, so it's sort of hard to navigate. But it starts as a blank screen, and each forecaster designs their own layout for how they want to forecast the space weather. And you'll notice this looks a little bit different than the one you just saw, and that's because we're actually looking at the sun in various wavelengths. So part of the job is looking at the sun in many different types of wavelengths, because different parts of the spectrum allow us to see different solar activity more easily. So you can see the eruption is so big that no matter what wavelength you're looking in, it's very noticeable. But most of the time, it's much smaller, and you need to look in multiple wavelengths to have a better idea of what's going on. And so this one, you can see the eruption here. And I like to mention too, after it takes place, you start noticing this really bright thing forming, and they look like bright, shiny loops. That's what's called a post-eruptive arcade. And I'm an architecture nerd, so I like that, because an arcade is a series of arches. You might find it like a Gothic cathedral, which I think is cool, because essentially what it is a series of arches where the sun is stitching itself back together. So it's such a big eruption that the sun tries to stitch itself back into one piece. And so going further down still, you can actually see, this is not a model, but actually what that eruption looks like. So behind that white circle is the sun. So this is a real image of the sun, and it looks so strange because we've actually just put a disk in front of the sun so that we can see its outer atmosphere, that corona. And so this is actually called a coronagraph. And so if you play through, you can see this huge eruption, all this plasma shooting out from the sun. So again, this is an actual observation taken by one of our telescopes called SOHO. This is the same thing, but it's closer in. So again, that white circle is the sun, and if I play through, you can see how powerful and huge these eruptions are, going back again. And it took just minutes after we saw it on the surface of the sun to see it in these images. However, it takes a few days for it to get from the sun to us. So once this happens, my job then is to tell people who work on our satellites. So they need to know what's going on, and they need to know how to react. So they can do one of three things when we tell them that there's a big solar event coming towards them. If they decide to take action, they can either turn their satellite off and lose a lot of data, so that's something they like to avoid because you don't get that information back when you flip it back on. They can put the satellite in sleep mode, like one might do with a computer. That's useful because then you can try to retrieve the information after you reboot it. But my favorite is you can actually turn the satellite away from the sun, so essentially it just gives it a kind of cute cold shoulder action. And I like that one because it doesn't lose any data, and it just turns its face away from the sun so that the expensive instruments collecting all the information don't get hit. And so what you're seeing here is the arrival. So this is a measure of how fast particles from the sun are hitting us. And normally it's around 300 kilometers per second. But when it gets to here, it spikes up, so we know something has hit. And because we saw it early on, this doesn't surprise NASA. We're expecting this. And so we can see this is the magnetic field now getting a huge shock to it. And so that's something we're ready for, and we're ready to forecast because we observed it earlier on. And lastly here, on the right, you see an image of our Earth in the middle. And this is where geosynchronous orbit is. So that's where a satellite can orbit above the Earth and always stay above the same location on the planet. So there are a lot of satellites here because people find it really useful to put a ground station directly below their satellite where it always stays above it. So this is a very popular place for satellites to live, and we need to know if our magnetic field ever crosses beneath it, because then all of these expensive satellites are exposed to the space weather that they might not be designed for. So this outer edge here, you might see on the right, that's actually the edge of the magnetic field. We call it the Magnetopause. And so as it goes in, you can see it gets smaller and smaller, and it actually touches the geosynchronous orbit. So that's another time I contact people working on our satellites, and I let them know about this development.